Hello everyone, my name is Akshay and I am a software architect at Geo Hotstar. In the recent past, our engineering teams took on an ambitious challenge. We completely retransformed how our users discovered content by building a conversation based discovery. Today, I'll walk you through our journey, the architectural decisions, the hard trade offs, and the rigorous engineering that went behind the scenes. Before we dive in, let's, let's see what motivated us to rethink content discovery in first place. We've come a long way from keyword matching to conversational discovery. The old mental model was different. It was users know what they want, give us the keywords, and we find matching content. The new mental model is different. Users today express intent, mood, context, and sometimes ambiguity. Our systems have to understand that, be it video streaming, e commerce, or our everyday digital interactions, users demand natural language understanding and deep multi turn context. Thus, the baseline for search has shifted to conversational now. Meeting this new baseline is hard enough in a vacuum, but we had to meet it under strict requirements of our business. Let's look at what those meant to us. As you see, our setup was extremely demanding. We are not just building an AI feature, but we are building it for a user base of over 500 million. At such scale, academic AI benchmarks go out of the window and ruthless engineering takes over. The product had to work seamlessly on both the homepage and live match stream. It had to support both voice and text in multiple regional languages. We had to move away from our legacy keyword match based search and go towards an LLM powered conversation based discovery. All of this right before a marquee business event whose dates could not move. Before we talk about our journey, let me show you what the final product looks like. Here's a look at the system live in production. Those of you who have the Geo Hotstar app can experience conversational discovery firsthand. As you see, the users can interact naturally either by speaking or typing. On the right, you see how the system gracefully handles ambiguous requests. Show me something I can watch on a weekend with my family. And it comes back with perfectly curated responses with intelligent follow ups. It also operates flawlessly on a live match stream. The users can pull up real time score, win probabilities, and playing 11s without ever leaving the match. I'm now at a point to talk about our engineering journey. And here's what to expect in the rest of slides as well. We'll talk about how we chose the right architecture, how we made it work at scale, how we measure and control quality, how we turned this into a platform, and finally, some of our learnings from operating this in production. Given this is a vast space, I'll not be able to talk about our ongoing journey, which is a native support for regional languages, our evolution towards a conversational assistant that can also take actions, and any fine grained optimizations that we are actively taking up. Before I go to the nitty gritties of architecture, I do want to touch upon a fundamental trade off that every GenAI application has to make. I call this the GenAI trade off triangle, the trade off between accuracy, latency, and cost. When building a GenAI application, you're constantly trading off between accuracy, latency, and cost. And the team must decide where they want to be on this trade off triangle. Example, they may not care about the latency and cost initially and only visit them while scaling it up. It's hard to improve all these three dimensions, and improving for just one exclusively degrades the other two dimensions. To take an example, while descriptive prompts, larger models, and more reasoning loops increase accuracy, they also degrade the latency and cost. For us, it is better to have a slower, accurate answer than a faster wrong answer. Hence, our mental model was to follow a strict priority: accuracy followed by latency followed by cost. While I say accuracy was most important to us, at our scale, we could not let the cost and latency also to drift away. Hence, all of these three have a first class presence in our evaluations. Here's a 10,000 feet view of our architecture as it exists in production today. On the very left, we start with a user query, which can be either voice or text. For voice, we have it run through device local transcription. Either way, the text query hits a crucial intent detection layer. It is on this layer a decision is made whether the query goes to a content discovery pipeline or a sports statistics pipeline. The content discovery pipeline is the one where the user may be looking for a movie or a show. Shah Rukh Khan 90s comedy movies is an example of one such query. The sports statistics pipeline supports queries where the user may be asking a question about an ongoing live match. For example, who hit the most sixes this IPL will go to sports statistics pipeline. Each of these pipelines have their own specialized components, which we're going to cover them in upcoming slides. Let us now go to the next level of details and talk about which approaches worked for us and which did not. Our initial instinct was to use a RAG, which stands for Retrieval Augmented Generation. In RAG-based systems, you take your data, give it to the model, and let it handle queries for you. However, this failed for us. Let us understand why. The conversational queries from users did not cleanly map to the keywords which we had in our catalog. Hence, we were able to find results like comedy movies, but not funny movies or courtroom dramas. On another attempt, we attempted to take this data and put it into a vector store. The retrieved results were too generic this time. And finally, giving our entire data and deep user context into the LLM was not a feasible option for us. Realizing that RAG was not enough, we attempted to give full control to the model. I call this approach model as the orchestrator. Here, we let the LLM drive the entire dynamic workflow autonomously. As you see, we start with these two inputs to the model: user query and the previous turn's context, and a master prompt with description of tools and their usage. It may call these tools in any order and any number of times. As you see, the model then calls our tools, which are the search tool, our sports stats tool, and trending contents tool. And finally, it composes a response which is sent to the user. While this approach is highly autonomous and flexible, it had a few problems. Only the bigger and expensive models were able to follow instructions in the master prompt. Thus, we had very high latencies, and that too with a high variability. So we took the control back from the model and gave it to software. I call this approach software as the orchestrator. In this approach, we stitch a static workflow using traditional software engineering, while enforcing fixed timeouts at each step. Again, we start with the intent detection step, which decides which workflow the query goes in. On the right, we have a stats workflow, which has a text to SQL step, followed by stats retrieval, and finally response composition. On the left, for content discovery, we have multiple parallel LLM invocations. Here, we gather data from multiple sources, have the combined output run through a retrieval and ranking layer, and finally, the end user response is composed. As you see, this approach provided the flexibility and control that we needed and had a highly predictable latency. This allowed us to focus on accuracy. Let's compare the static and dynamic workflows side by side. The dynamic workflow, where the model dictates the flow, is low predictability, has highly variable latency, is dependent on fragile prompt engineering, and that too with a low instruction compliance. Conversely, the static workflow, where code dictates the flow, offers high predictability, strict timeouts, and robust software defined control. As you would have expected, we decided to go ahead with the static workflow for our production. I also want to make a call out here. We are still exploring the dynamic workflow. With the new and recent models, we see promising improvements in tool usage and latencies, and all of them are on our radar. We're also exploring the dynamic workflow as we shape conversational discovery to a conversational assistant that can also take actions. I want to spend some more time on the static workflow, given this is the one we went in production with. I'm going to trace a query end to end through the layers of static workflow and see what happens behind the scenes. Let's start with the user query, mood kharab hai, show me something I can watch for dinner. As this query hits the intent detection layer, it is rightly categorized as a content discovery query. If you remember, we had multiple parallel LLM invocations in the content discovery. Here, I'm only showcasing two for the sake of simplicity. So in the first step, the LLM identifies the mood setting and the mood setting and the theme of the query, which comes out to be relaxing, heartwarming, and feel good. In parallel, we ask the LLM itself to look at the query and give us some titles based on its word knowledge. Now, we may or may not have these titles in our catalog, and we'll do that exact check in the next steps. As you see, the merged results contain Good Luck Charlie and The Office Now. We just use the information from previous step, hit our keyword matching based retrieval layer, and got these merged results. The merged results are now run through our personalized ranking layer, where we re-rank these according to users' taste preferences and watch history. Finally, those results are sent back to the user in a humanized way. Here are some light, feel-good options that are perfect for dinner time. Look at how it relates back to the original query which the user had. So far, we've discussed our major architectural decision, the choice of orchestration. Let us now talk about how we made it work at scale. Turns out, it was not a single decision, but a stack of decisions which helped us scale without burning our pockets. We're going to talk about each of these one by one. With the flexibility of software orchestration, we right-size the models for each step. We use small and fast models for basic decisioning like intent detection, and use bigger and expensive models for complex reasoning like text to SQL. With dynamic orchestration, the choice of model was only one, and that had to be a bigger model for prompt adherence. In a way, breaking down the LM interactions in the static workflow also helped us scale. We also took up a couple prompt optimization techniques. We made sure that we only send the bare minimum details to the model and from the model. This allowed us to keep input and output tokens in check, reducing both latency and cost. Second, we also cleverly organized our prompts so that the dynamic part of user query is always appended. Turns out that this is very cache friendly to the LLMs, and it helped a lot in managing latencies. We use a battle-tested JVM runtime for our agent implementation. This implementation uses highly performant async IO, which was written using Spring Webflux as the framework. Finally, instead of going to multi-model LLMs, which accept voice as input, we used Android and iOS native speech-to-text models. These on-device models are both free and fast. I want to make a call out here that we are actively moving these models to the server as we want to support regional languages in a better way. Choosing the right architecture and scaling it was only half the battle. The other half was knowing if it actually worked. I'm now going to talk about how we measure and control quality, the evals. Evaluating a product like conversational discovery requires capturing a vast continuum of query complexity. This continuum goes all the way from precise and simpler intents to multi-turn, highly imprecise conversational queries. To cover the full ground, we adopted a multi-tier dataset preparation strategy. We curated data from these three sources. One, a product and data science teams curated seed sets. Two, anonymized production samples. And three, synthetic data generated using LLMs themselves. Then, based on which queries are most important to us, we categorize these into golden, bronze, and silver datasets. We call these multiple tiers of datasets. The datasets which were created in the previous slides, they then run through an evaluation pipeline where another LLM, another unbiased LLM, acts as a judge and grades the responses received from our system. This judge produces metrics on accuracy, relevance, and factual correctness, while a tracing gives the details of latency and cost. Having a holistic evaluation view was so important that we created an internal tool for it. Let me show that to you. We use GenAI itself to create this tool in-house. As you see, the tool allows for comparing and visualizing our most important metrics: accuracy, reliability, latency, and cost. Here's another drill-down view which shows the depth of metrics. Accuracy specifically has many dimensions: intent accuracy, retrieval coverage, factual correctness, response relevance, and multi-turn coherence. Each evaluation run also sends out an alert, which has actionable numbers right in Slack. This screenshot shows primary and secondary metrics for a silver evaluation run. The reports in these alerts are used to make a decision on whether or not the current artifact makes to production. Putting something in production once is not the end of journey. We needed to iterate every day on our solution. This is where platformization plays a huge role. This project had unique challenges. Our evaluations were heavily dependent on the quality of data fed to it. In order to ensure that our evaluations represent reality and do not give us a false sense of safety, we created an isolated staging environment for it. As you see, the staging environment continuously syncs from the production catalog. It also had a mock statistics database and a live match simulations capability. Staging environment, in conjunction with the prompt registry, which we are going to cover next, was the core of reliable evaluations. Once prompts and models become production dependencies, they need the same discipline as code: versioning, evaluation history, controlled rollout, and rollbacks. Hence, we invested in an in-house prompt registry. This registry not only keeps the version of prompts and models, but also allows us to run A/Bs and change the model at runtime without code deployments. It was not a fancy system, but a very simple one built using Git, S3, and some conventions enforced through code. Let us now see how the staging environment and prompt registry work together in a CI/CD loop. I'm sure all of us have seen the CI/CD for traditional software. The key difference from a normal CI/CD is that a prompt or a model change can greatly alter application behavior. So every prompt or model change has to pass evals before it reaches production. Going from left to right, we have this continuous loop where first, a production catalog and ground truth is synced in staging. Thereon, bronze, silver, and golden datasets are run through our evaluation pipeline. And then, evaluation reports are generated, which are pushed through Slack alerts. It's only verifying the evaluation metrics for no regression that the artifact is allowed to make to production, and that too only via prompt registry. Operating this system in production also gave us some useful learnings. I'm going to cover them next. The production environment taught us these lessons. Trace before you evaluate, guardrails are product requirements, structure and fallbacks bring reliability. Let us understand why they are so important. Attributing failures in GenAI systems is very hard. If a response receives a bad score, was it an intent failure, a routing misfire, a retrieval error, or a model hallucination? The two of our golden rules have been trace before you evaluate and iteratively build simple layers. This is grounded in our learnings. On one occasion, we were unable to debug a production issue of irrelevant responses. We then had to shut off our layer of personalization, enhance our tracing. It's only after the retrieval layer was validated end to end were we able to bring back the layer of personalization. When operating a product like conversational discovery for hundreds and millions of users, guardrails are absolutely non optional. In fact, as the title says, guardrails are product requirements. Our initial prototypes could be nudged to talk about religion and politics. Hence, there was a need to ensure that every output is strictly brand aligned, even under massive public scrutiny. To achieve this, we implemented tripwires at both the ingestion point of the request and at the emission point of the response. These tripwires have hard filters that manage all kind of sensitive outputs. Now let's talk about how we make this system resilient in production. Some of our hard learnings have been about compatibility and fallbacks. When we initially used text mode in the model, we often ended up making a prompt and agent out of sync. Hence, we enforced a JSON contract with a schema validation between the prompt and the software. Once we did that, we never ran into compatibility issues ever again. Even the best of models have downtimes. If not downtime, we have seen our rate limits getting breached. We all know all prompts and models do not universally work with each other. Hence, we cannot fall back to a random model in production. Hence, we ensured that all our fallback paths are pre-evaluated model and prompt combinations. We've covered our agenda for today. Bringing all of these together, let us summarize the key takeaways from our journey. If you could take away 3 things today, make it these. First, at scale, software control beats model autonomy. Second, platformization speeds up reliable delivery. And third, for GenAI, tracing, evals, and guardrails are non-optional. And finally, the key being, scaling a GenAI application is ultimately an exercise in rigorous software engineering. Thank you for your time and attention today. I would now like to open the floor for questions.
So I
Yeah.
haven't worked with the agentic flows at the moment. I have had some personal experience. I
Mhm.
want to understand your thought process around how should we navigate, what should we rely LLM or orchestration on, and what should we rely our own knowledge and software engineering. Where should we apply our own workflows? How do we do this decision making? And yeah, primarily that.
Yeah, I think we also navigated this trade-off. If you remember, initially we gave everything to the model, and we only chose a static orchestration when it was not working for us. One, LLMs are very new, so we can't just simply and blindly rely on them. So whatever you do with them, also have a validation step, maybe an unbiased LLM that validates what the original LLM did. And marrying these two together, you'll be surprised the kind of accuracy it gives to you.
I thought RAG would provide you the context, right? I mean, so what?
Yeah, so there were 3 attempts. Initially, when we attempted RAG, so RAG says, hey, take your data, give it to the model, and let it handle queries for you. But you can't just take your entire data in one shot and give it to the model. So you have to have some kind of index or a filtering layer before it, right? So we attempted two kind of indexes. One, which was our initial keyword match based index, which will find out the right documents from the initial query and give it to LLM. This didn't work for us because the keyword matches in our, so it was an open search index. It didn't give good results in the very first cut itself. Now, if you give 3 initial bad retrievals to the LLM, it can't do much with it. Secondly, we also tried creating embeddings and putting it in a vector store. This time, the problem was that it matched too many things in a generic way. So the accuracy of what we give to LLM was bad. Hence, we had to choose to control what we give to the LLM so that it can then operate on it and give you a humanized response back.
But where did you get the, the user preference, the context?
Yes, we because at Hotstar we are anyways doing personalization. We have the user preferences and context in our data stores. We also have the catalog. The LLM does not. So we somehow have to give these two things to the LLM if we are building a RAG-like approach. Does that answer your question?
I will probably pick it up later.
Okay.
And the other question I have is, what were the challenges when you were building the evals?
Yeah, pretty interesting. And I think I've not done enough justice to the evals here. Um, evals are the unit test or service level test for a GenAI system. And honestly, we had multiple layers of challenges. So given when you're exposing this to a consumer facing app, the query can be anything. You can talk about Virat Kohli, Narendra Modi, or anything. You can pretty much give any English to it. Hence, to come up with an initial evaluation test, that itself was a large challenge. Our traditional search, people will come and only give us keywords. They'll not give us English sentences. Hence, as you see, a lot of human judgment, our analyst teams, our data science teams, they created these seed sets, which became a core of our evals. Secondly, turns out the LLM themselves, they can generate these queries because they have knowledge of how the chatbots of the world are operating. So you can say, hey, I'm building a recommendation-based chatbot. Give me a list of queries that people can ask it. So these two things, and based on some expansion of these seed sets which we had, and then finally a human judgment layer of curation. As you saw, the bronze, golden, and silver data sets. There's a lot of time that went into curating them. But once we did that, our evaluation cycle was kickstarted. Then, and we also released it slowly in production. So as we see these new insights from production, we'll add them back to evals, and that's how the cycle is running today.